for joining us on day 3 of our training on HPC programming for AMD GPUs. Today we have profiling tools and MPI communication libraries. So we're going to start out today with all things MPI. So we're going to talk about checking the performance of MPI and a typical use case of stencil calculation, exchanging data. Giacomo is going to lead off with the GPU-aware MPI talk, and then we'll start into the profilers with Luka. And so take it away, Giacomo.
Thanks, Bob. Hi, everybody. Good morning, good afternoon. I think my voice is going down a little bit, so hopefully it's gonna hang in there for this presentation and the last one. Okay, yeah, so as Bob said, this is what we're gonna start with, so let's just dive into it. Okay, so we're gonna take a look at what it means to have GPU-aware MPI, and specifically we'll take a look at point-to-point communication and collective communication. I'll show you some examples where we have measured the bandwidth and the latency of some GPU to GPU communication in different settings. And then we're gonna make a special mention to the case for MI300A, and then we'll finish up with something quick on recall, and then we'll take a look at the ghost exchange example that's using MPI. Okay, so what is MPI? I think that most of you might already be familiar with MPI, which stands for Message Passing Interface, and it's fair to consider it the de facto standard for communication in high-performance computing. And basically, the difference between, for instance, OpenMP that we have already discussed in great detail in the previous 2 days, and MPI is that with MPI, you have distributed memory, so it's not shared. So each MPI process has a private address space, and the memory that's assigned to that process cannot be reached and modified by the other processes. And therefore, if you want two processes to communicate, you'll have to do a message exchange, basically, so that you can pass that information. And the process of this is that it's a lot harder to step on each other's toes, as you may instead have with shared memory, where the risk of race conditions is a lot higher. And also, this paradigm for MPI makes it very viable for using it to communicate across nodes, for instance, through a network. And so MPI is for these reasons used at, I would say, almost all HPE clusters to do communication. And yeah, so MPI is an API. So this means that you can find different implementations of it. And also MPI doesn't really put any specific boundaries on how you actually implement this message passing, and therefore there are different ways that can be done. So in terms of having GPU-aware MPI, this refers to the ability to pass the GPU-allocated buffers to your MPI calls. Because in general, what you would have to do normally would be to copy the buffers from GPU to CPU and then pass those to MPI. For instance, if you're already familiar with MPI, you can use, for instance, an MPI send, which means that you're going to be sending some memory to some other process, and Normally, that buffer that you pass to the MPI send would have to be on CPU, but with GPU over MPI, you can pass the one that's allocated on the GPU, for instance, with heap malloc. And this is what happens in practice when you do that is basically the CPU is bypassed in the communication, and therefore the GPU buffer is used without any copy. And I mentioned before that there's different implementations of MPI. In our system right now, we're using OpenMPI, but you know, if you're on an HPE system, you may be familiar with Cray and Pitch, and there's also MPA-Pitch, for instance, that supports GPU-aware communication. Okay, so in terms of what makes GPU-aware MPI possible, that is the GPU direct RDMA technology that provides the feature of basically bypassing the host so that the network adapters can directly access the GPU device memory. Different implementations of MPI may or may not use GPU direct RDMA. And we have to be clear on the difference between what is the technology that makes that possible and the API, which is just MPI in this case. Okay, so after this warm-up introduction, we're gonna take a look at some code here that's focusing on the case of a discrete GPU, so where you have separate memory space for CPU and GPU, which is the most frequent case you'll be in. So here we're focusing on a point-to-point communication example where basically we have two processes that are communicating with each other. So in that case is point-to-point. So you've seen most of this already in our heap presentations. So we are allocating memory both on the host with malloc and on the device with heap malloc. Then we are doing some initialization that's different depending on the specific MPI process or MPI rank we're on. See that there's an if condition on the rank. And by the way, you can use the MPI API to get what the rank basically. So when you execute your program with MPI, the rank will be different depending on the process you're on. And so you'll get on either two of these if conditions. So there's a mem copy that after the initialization is done on the host, copies that to the device. And then you see here, this is the key part for GPU aware MPI. We are passing the D underscore buff, which is the one that lives on the device. And then basically we're just copying back and checking that nothing unexpected has happened. As we said before, if we did not have GPU aware MPI, then we would have had to pass just the host buffers here. So in this case, you see we initialized on the host and then copied to the device. So this copy from device to host in this specific case was not really necessary since the initialization on device copied the one from host. But in general, if you didn't have GPU aware MPI, then yeah, you'll have to copy to host first and then pass those buffers. Okay, so this is a case of a collective communication where basically we are using the MPI reduce. So the idea here is similar. We are allocating on the device, and then we are using those buffers for the collective communication and then checking our results. Okay, so now we're gonna look behind the scenes and see what's happening specifically in the topology of our hardware because we want to have more knowledge of the bandwidth that we can get with the GPU to GPU communication. And also we want to make sure that the results that we get are what we should expect. So what I'm about to show you is a good set of health checks on your system and your MPI installation to make sure that the performance that you get is actually the one that you should be getting in theory. Okay, so now you have heard of ROCm SMI, and that comes with your installation of ROCm, sits in the bin. And if you run it with the dash dash show topo option, it'll show you the topology of your system. So you'll see here on the left, this was for an MI210. So it's showing 8 GPUs. And it's also telling you to which NUMA region each of those GPUs belongs to. So GPUs from 0 to 3 are in NUMA region 0, 4 to 7 in NUMA region 1. Something else that's very relevant to our discussion is that you can get the links between two different GPUs. See that GPUs in the same NUMA region are connected with each other with the XGMI links, which are the high-speed links. And those that are not in the same NUMA regions then are connected with the PCIe. And this table down here also tells you the number of hops between two GPUs. So in case you want to communicate, you want to have GPU 0 communicate with GPU 1, 2, or 3, there's only one hop because they're in the same NUMA region. For 3, 5, 6, and 7, GPU 0 will have to do 3 hops. And you can already tell that the more hops you have to make, the less performance you'll have. Okay, so now we want to look at what happens in terms of bandwidth when we're doing intranode GPU to GPU communication. So basically, we have one node and we want to see the bandwidth that we get when we pass messages between two GPUs in that node. I think we've already mentioned the environment variable heap visible devices. You've seen in the heap presentation that you can set the device you want to work on in your code, but you can also do it before running, basically, just by setting this environment variable that's gonna make some GPUs hidden to your code and others visible. And in this case, since we wanna measure the communication between GPU 0 and 1, those are the ones that we make visible with heap visible devices. And notice here that we're going to be running MPI leveraging UCX, which is a communication library that's intended to basically optimize the backhand of your message passing. So we have our script in the HPC training doc repo that installs MPI with UCX and with UCC, which is a library for optimizing collective communication. And therefore, if you want to leverage UCX when you run with MPI, you'll have to include this option here. Okay, so and notice that here, so this is the OSU micro benchmark, which is what's often considered a good health test for your system. So here we are gonna measure the communication between GPU 0 and 1. You see that they sit in the same NUMA domain here on the left, and they're connected with XGMI. So we can expect a high bandwidth in that case. And see that here we get 41 gigabyte per second. And if we look at 0 and 4, we know that they're in different NUMA regions and they're connected with PCIe, which is the general purpose link that's slower than XGMI. And in fact, you see that we get 25 gigabytes per second. Okay, so in terms of the options that you can leverage to perform GPU to GPU communication. On our GPUs, there's two options. You can use the SDMA engine. And the pros of using that is that you can overlap communication with computation. However, you'll see that the bandwidth that you'll get compared to the other method that I'm going to introduce is actually a little lower. The other method is with the bleed kernels that basically launch a kernel to handle the communication, and you'll get a higher bandwidth with that, but then you're not going to be able to overlap communication with computation. So let's take a look at the case of the expected bandwidth that we can get in this case of Frontier. So this is the layout for Frontier that has MI250X GPUs. So see that the GPUs that are closest to each other are expected to have the faster bandwidth here. They have 4 links. And then the others are displayed here in the slide. So basically, we're gonna take a look at what happens with SDMA or bleed kernels in this case, and we're gonna check that the bandwidth that we get is, or I should say, we're gonna check if the bandwidth that we get is comparable to the theoretical expectation. Okay, so this is on Lumi that also has 250X GPUs. So here Lumi has an HPE, it is an HPE system, so they have the Cray stack. So here we're loading ROCm, but also we're gonna be using Cray and Pitch instead of OpenMPI. And then see to enable bleed kernels, what we have to do is to disable SDMA basically. So here we're gonna export HSA, enable SDMA and set it to 0. And then once again, we're gonna be using that OSU benchmark. Notice that we're using srun intranode, so the node is just one, 2 processes since we're interested in doing point-to-point. As you can see here, PT to PT, that's point-to-point. And then every time we set different visible devices, because that's what will make the GPUs that we want to compare visible. So see 0 and 1, it's getting us 142, sorry, what's 0, 1? 0, 1 is getting us 142 gigabytes per second, which is very, very close to the expected one, that's 145. And then we have, for instance, 0 and 6, that is here, you see, we're getting actually a little higher than the theoretical here. So that's very good. And then let's see, for instance, 0 and 5. 0 and 5 is over here. And so we're getting around 45 gigabytes per second. So with the bleed kernels, we're getting very, very close, in fact, to the expected bandwidth. So what happens with SDMA? So now we're gonna export HSA, enable SDMA, and set it to 1. And you see that you see it right away between 0 and 1, the bandwidth actually goes down by quite a bit. So we would be expecting 145 gigabytes per second, but instead we're getting close to 50 gigabytes per second. So with SDMA, as we said before, the bandwidth that you'll get compared to the bleed kernels is not as good. Yeah, so this slide here is just giving you a visual representation of what we have just seen, put it in a table. Okay, so the next one is measuring internode GPU to GPU communication. So see, we're still doing point-to-point, but now we are using 2 nodes. So capital N is set to 2. And this plot here that was done on Lumi is basically increasing the size of the messages that we are passing and measuring how that has an impact on the bandwidth. And see that the more the messages increase in size, the better bandwidth we get. So it's important to well, it's important, you know, if it's relevant to your application, and if you can, having larger size messages will help you get the best bandwidth. Here we're talking about internode. So we want to show that, as expected, this is a collective communication or reduce. It's expected that if you're working across nodes, then you'll have more latency. So here we're comparing the case of running with 8 ranks in total. But in the first table, well, the first display that we have here, we're using 2 nodes and 4 ranks per node. And in the one below, we're using just 1 node, and so all the ranks are on that node. And you see that, as expected, the latency for the internode is higher. Okay, so now going to the case of MI300A, we're doing the same Broadcom SMI dash show topo as before. And you see that in this case, each GPU, so we have 4 GPUs on 300A, each GPUs has their own NUMA region. But interestingly, all the GPUs are now connected with the high-speed links XGMI. I think we may have already mentioned it before, but it's very important to leverage GPU-aware MPI to have heap malloc be used for the allocation. Because if you think about it, with MI300A, we said already several times that you don't have to use the device buffers. And so that's very helpful at the beginning. Say that you have your CPU code, so you have all host buffers there, and you want to start porting, so you don't have to worry right away about doing the explicit memory management. You can just pass your host pointers to the GPU kernels. But then, if you want to leverage GPU-aware MPI, you're going to have to pass the device buffers to the MPI calls. So you have to be aware of the fact that, you know, maybe after you've ported your code to MI300A, maybe it makes sense, first of all, for portability, to include explicit memory management, and also to make sure that you're leveraging GPU-aware MPI because you're using heap malloc. So this example here is showing you that if you don't use heap malloc, if you just use malloc, then the bandwidth that you get is a lot worse. This is once again point-to-point communication. And you see, with heap malloc, you get 90 gigabytes per second, and with just malloc, just 22. So it makes a lot of difference. Oops, sorry, went back. Okay, so a brief mention of RCCL here, which is the ROCm Collective Communication Library. As the name suggests, it's a library that's specialized on collective communication. So basically those where all processes kind of operate into some operate towards getting a unified result in a way. So for instance, you know, all reduce means that all of them will reduce to a single scalar. For instance, you know, you may be doing that for a reduction. There's an all gather, the broadcast, where one is sending to everyone. So yeah, so it's a library for optimized collectives, and it's becoming more popular as AI is becoming more popular because it's used as a backhand for the collective communication for AI applications. And RCCL is a fork of Nickel from NVIDIA. And as we discussed yesterday, they strive, the Rico developers, they strive to maintain the same API as Nico to facilitate porting. Okay, so if you want to play with Rico a little bit, you can clone this Rico tests repo from the Rockam repo. And basically, you can run it like this. Here we're showing you just the case of an all reduce. Remember that these are the parameters that you can play with. So you can decide the size of the messages and, for instance, how many GPUs you want to run with. And down here, this is just a little snapshot of what you can expect in terms of output. Okay, so before I move on to the Ghost Exchange example, let me just summarize here real quick. So we talked about MPI, what it means to have GPU-aware MPI, what's the technology that enables it. We mentioned that MPI is an API, so you can have different implementations, and you've seen, for instance, Cray and Pitch be used here. As well as OpenMPI. We've talked about the OSU micro benchmarks and how you can use them to kind of check that your system is behaving as you expect. And then we have discussed how having MI300A will have you kind of make some considerations on what you're doing to check that you are getting the most performance. And then we've just seen recall. Okay, so there's a bunch of exercises that you can run on our training examples repo. As you can imagine, they just sit in the MPI-examples directory. So you'll get, there's a README there that you can take a look at on how to run the exercises. Notice that there's this export here of the compiler, because you can override the underlying compiler for OpenMP with the wrapper. And our modules for the compilers, when you load them, they'll do that for you. But if you're working with Fortran, then it's a little trickier because you need the modules to be compiled with the same compiler. So we have provided a separate MPI installation for the AFAR module. So you'll see if you load Rockam-AFAR, you'll see that the compiler modules show up as well as the MPI module. Okay, so yeah, so this is just how you run those OSU benchmarks. So I'm not gonna go into much detail since all that info you kind of already seen, plus it's on the README. And this is showing you how to configure as well, but you know, we have all the info in the repo. So just notice here specifically that we are enabling Rockam and then passing the Rockam path. Okay, so next up is a mention of this Ghost Exchange MPI example. So basically, the Ghost Exchange example here is intended to be a simplified example of what an actual real application code using MPI might look like. And the reason for providing this is kind of to make available something that can be used as a testing ground that can be compiled quickly and run quickly, but still has most of the features that you'll see in an actual code that may or may not compile or run quickly. Okay, so the problem at hand here is we have a rectangular domain that's been discretized with a Cartesian structured grid. And we are initializing the solution on the domain, and then we are advancing it with a kernel that's just basically doing an average of the solution using the neighboring cells. So the solution is defined on a cell-wise fashion, so each cell has one value for the solution. And the averaging kernel is what we call a blur kernel. That is basically just a 5-point stencil that's taking the information from the cell at which you're advancing the solution and at the 4 neighbors, since we have rectangular cells, and then it's just summing them all up and dividing by 5, basically. So why do we talk about ghost exchange and what are the ghost cells? So when you run in parallel with MPI, you have to think that in most cases, you have mathematical operators such as the blur kernel that I described that have a so-called stencil. So if you compute on your own cell, on the cell that you want to advance your solution on, you'll need information from cells that surround you. And you can tell that if you're running with MPI, basically you are partitioning your domain and assigning each chunk to a different process. And we said that the memory is distributed, so different processes cannot access information from other processes unless it's sent to them. But what happens is that we basically enlarge the MPI domains so that we give them the so-called ghost cells that basically surround the domain and form a halo. So sometimes they're also called halo cells, and in a way that the MPI process can read the information on those ghost cells, but it doesn't have the privileges to actually modify it. So the only way you can modify them is by receiving a message from the process that actually owns them. And the reason why they're called ghost is because when you run in serial, they don't exist. They only show up when you run in parallel. Okay, so the process of doing the halo exchange with MPI is basically the process where you call MPI and pass information across processes so that the values at the halo is up to date, so that when you go and advance your solution, you're going to be using the correct values. So see here, this picture is taken from Bob's book, and it's showing you this ghost exchange process. See that we have a domain composed of 12 cells on the x-axis and 12 cells on the y-axis, and it has been partitioned among 9 MPI processes. So see that the cells that have a dashed boundary, those are the ghost cells, and the ones that have a solid boundary, those are the ones that are actually owned by the process. And this is showing you that the halo exchange is done first on a left to right fashion. So processes are exchanging first with the ones that own domains to the left and to the right, and then it goes up and down. So they look at the neighbors that are north and south. We have 2 different implementations of the ghost exchange example, one that's done with OpenMP and one that's done with HIP. And the idea was to begin with a CPU-only implementation and then add progressively implementation improvements to make the performance better, but also to highlight new flavors that you can give to your code. So the way it goes, it starts from an example that's called Orig, which is just a CPU implementation. And then, for instance, version 1 adds the offloading to the GPU using OpenMP in the OpenMP case. And it's leveraging the APU programming model. So we're exporting HSAXNAC equals to 1. Version 2 is adding the rocTX markers so that you can see those regions that have been enclosed with the markers on your profile. Version 3 is allocating the buffers on the GPU using the OpenMP API. And then there's other improvements that you can do. I'll talk about 4 since it's one that we're gonna look at. So with version 4, the communication buffers are dynamically allocated on the CPU only once at the beginning of the run, instead every time the ghost exchange call is performed. And then with version 6, we are doing explicit memory management. So we're not using unified share memory anymore, and therefore you can unsec the HSA XNAC variable. Orange 8 is an interesting example to look at because um, it's still all CPU, but we have modified the way the solution is advanced so that it's done in an asynchronous way. Basically, you first advance the cells that do not need the halo information, so basically the ones that are in the interior of your MPI domain, for which the stencil doesn't need halo cells. And during that advancement, you also perform the MPI communication. And then, sorry, not, I gave you a spoiler, not during, right after you perform the MPI communication. Um, and then you advance the cells that need the halo. So I said during because in the heap implementation, actually, we are porting to GPU that Orange 8, and we advance the solution that doesn't need the halo on the GPU at the same time as the MPI communication is happening on the CPU. So if you run ver8 for the heap implementation, you'll see that if you open a profile, there's going to be overlap between solution advancement on the GPU and MPI communication on the CPU. So there we're using the CPU buffers, not the GPU buffers. So in that case, we're not using GPU over MPI. But the reason for that is because we are in the case where we're leveraging unified share memory, and therefore we don't want to make data movement from CPU to GPU. And so we use everything on the CPU as well as the MPI communication. So for heap, as I said before, the versions move along pretty much in the same way. So version 1 is also the case where we're using heap to offload to the GPU and using a unified share memory framework. Version 4 is also a case where we're dynamically allocating outside the call for the ghost exchange function. So it follows basically the same recipe that you had for OpenMP. Okay, so if you want to run it, this is how you do it. You should load the ROCam module, AMD Clang module, and OpenMPI module. And then the thing to keep in mind mostly is the parameters that you need here to run it. So -x, -y, basically they specify the MPI partitioning. So you have to make sure that what you give to X and Y, if you multiply those two, it gives you the number of processes that you want to run with. So basically -x2 means that you're partitioning the X direction in 2, the Y direction in 2, and so you end up with a grid of processes that are basically getting the northwest, northeast, southwest, southeast regions of your domain. And you could also do -x4 and -y1. In that case, you'll have 4 vertical strips as your partitioning. -I, -j, they specify the number of cells. -h is the size of the halo. So for the blur kernel, you just really need size 1, so just 1 layer of cells around your domain. But if you had higher order operators, for instance, you'll need more. But you can also play with this -h and just make it bigger if you want to see the effect of increase the communication when you run it. -c is to include the corners, and -I is just the number of iterations or time steps that you want to do when you perform this. Okay, so I should give you a heads up. So here I'm showing you the OpenMP and the heap implementation side by side, but I'm not trying to do a comparison between the two. I'm mostly interested in showing you what specific improvements you get for each of those separately as you move up in the version number. And you see that in what I'll show you, actually, OpenMP performs better than heap. But we haven't really spent time profiling and optimizing either of these two, other than showing you what implementation improvements we do with the versions. So we can certainly go ahead and optimize the heap kernel, the heap kernel's version to make it better than it is. So this is just a disclaimer, and I'm advising you to not get too hung up on the comparison between OpenMP and heap, but rather focus on the changes that you see for each of those going up in the version. Okay, so this is the OR edge, which is the same for either case, since this is just CPU. So you see that the total time is 25 seconds, around 26. And when you offload to the GPU with OpenMP, now you know that this here is the blur kernel, the one that I told you about at the top left. See that it's just an average. And if you want to offload that to the GPU with OpenMP, you'll do this pragma-mp, target teams distribute parallel 4. And notice that we're also using the collapse because we have a nest loop. With heap, this is how the kernel will look like. We have a two-dimensional grid of threads. See that we have the .x and .y. And this is how it will look with heap. So the next improvement that we want to show is going from version 1, so offloading to the GPU, to version 4, where we are allocating dynamically the communication buffers once and for all, and not every time we call the ghost exchange function inside that function. This is done for both versions, and you see that the improvement is not gigantic, but you can still see it. So for OpenMP went from 5.6 to 5.3, and for heap it went from 11.8 to 11.05. And then the other comparison I want to make is between version 4 and version 6. So with OpenMP, we are doing now the explicit memory management. So we're gonna, add a ton of maps for OpenMP, and we're gonna also have, not a ton of maps. We're gonna, what I meant is we were gonna leverage the data environment. So you see, we talked about it yesterday. So there's gonna be some enter data maps, so that you can have the data be resident on the GPU for as long as you need it. And so you don't have to always copy it back and forth. And see that the time basically gets cut in half with OpenMP, and pretty much the same with heap. We're gonna insert a lot of allocations on the GPU with heap malloc, and then you may have some mem copies as well. Okay. So the last thing I wanted to show you is something that I think is very interesting, because it's a way for you to get extra performance basically without doing anything, without modifying your code at all. And that's just by leveraging the knowledge of your hardware through affinity settings. So if you run version 1 for heap, you'll see that this message gets displayed, and this is telling you that you are running with 4 ranks. It's telling you the hardware thread that the process ran on. And this in the middle here is telling you what GPUs are available to the process. So we didn't tamper with this. So you see that all GPUs are available to this process. And there's no binding between the GPUs and the ranks. So since we didn't specify anything, all the ranks will run on the default GPU that is GPU 0 in most cases. But you can change that and run your script with this set GPU device that's gonna bind your MPI ranks to a specific GPU so that you can have one rank run on one GPU and then a different rank run on a different GPU. And the way you bind this is normally by looking at the LS CPU information so that you can pick the rank that's gonna be closest to your GPU. So here you see the GPU available to the processor now, not all of them anymore. And we are binding process 0 to GPU 3, process 3 to GPU 0. And just by doing that, so we just changed basically the way we execute this code, we got a 3.66x speed up. So that alone can help you a lot. So yeah, so this is it for this presentation. Hopefully you found the MPI Ghost Exchange example useful. There's a lot to play with there, a lot to explore. And you know, let us know if you use it and what you think about it. Thanks a lot.
Thank you, Giacomo. So that's our first talk, and we have until 2 p.m. for exercises. So just shy of 10 minutes, and then we'll go into the next presentation. Questions in the Discord. Could you explain passing GPU buffer to MPI slide 19?
Let me pull that up real quick. Oh yeah, so basically here, see, we are on an MI300A system, so we are just comparing what happens if you have a situation where you are doing the point-to-point communication, but in one case you supply to the MPI send and receive something that's been allocated on the device, so with heap malloc. And on the other case, you pass something that's allocated on the host, so with malloc. So for instance, if we go up here in that original example that I showed you, so the first case would be basically this that we're showing here. See, the MPI send and receive have the device buffers. And the second case would be the case where instead of passing the D underscore buff, you'd be passing the H underscore buff, which has been allocated with malloc.
Yeah, but this is with the MI300A, so it has a single buff pointer. And on the 300A, what will make the difference is what the original allocation was done with. So if you did the hip malloc, it is like that debuff example. If you do the malloc, it will be like the system allocator version and HBuff. So that was one of the questions we had early on the MI300A is since there's only one pointer, which method is it going to use? And this is a demonstration that it's going to use the whatever the original memory allocation was.
Yeah. So I see Francois is talking to Luka. So there should be an MPI installation for all the ROCm and ROCm FR.
But it's
So,
not to load ROCm. It's a hierarchical modules. So
Yes. Yeah, first load ROCm or ROCm FR, and then you'll see the ones that depend on them.
yeah, it adds a little confusion doing the hierarchical modules, but it also keeps you from seeing 500 modules and knowing which ones are valid. Luka, you want to go ahead and test your share?
Yeah, and everybody, make sure that you are on a compute node when you want to do computations, because the login node doesn't have GPUs.
I guess you can see my screen, right?
Yeah, you're good.
Yeah.
We'll give them a few more minutes
Sure.
to try out exercises.
Thanks, Luka, for tackling some of the questions. It's good to see you on the chat and on WebEx, of course.
Okay, we still have nodes available on the AAC6, so go ahead and try some of those examples when you have a chance. I am going to kill a couple jobs here that have been running for days.
Those jobs just like it. They want to be there. They want to leave.
Yeah. If you do want to run something longer than our eight-hour queue time, please let us know why you need that time. We try to keep heavy loads off this system since it's meant to just experiment with light loads and compiles.
And also, be careful because if you allocate multiple nodes, then you're gonna have to use srun instead of MPI run. Otherwise, MPI run will not will complain.
Yeah, we have some issues with the build of OpenMPI on this node because there were a lot of leftover PMIX packages on the system and it's causing conflicts. And we don't want to completely rebuild everything and maybe end up with nothing. I do want to, before Luka starts here, I'm in between each talk, I'm going to remind you that we're going to have a poll that is going to be posted. I don't know if Maria's already posted that or not, but we do ask you to respond to the poll and give us some feedback so we can improve the training workshop materials. So Luka is in Munich and works with the Max Planck Center or Compute and Data Facility at MPCDF and does quite a bit of profiling support there. So he's been working with the profilers and helping getting those working properly and identifying what issues there are with them. And this is a really nice presentation of using timeline profiling. So let's turn it over to Luka and give him our attention.
Thank you, Bob. So today I will be presenting 2 out of 3 main AMD GPU profiling tools. 2 that are used for the GPU timeline profiling, while in the presentation after mine, I believe Bob will talk about the going in depth into GPU kernels. So basically what I will be talking about today is first rocprof-v3 tool, which is for the GPU tracing and counter collection. And then I will follow up with rocprof-sys, which is can be seen as rocprof-v3 plus much more. So this not only for the GPU tracing, but also for the CPU tracing. Both of these are using under the hood SDK library for tracing and profiling. However, I will not go into detail about this library. This is more for the people who are interested in writing their own profiling tools. And then finally, in the following presentation, Bob will talk about rocprof-compute. Okay, so rocprof-v3, let's start with that one. What is rocprof-v3? Well, it is a performance analysis tool for ROCm-based applications. It can be run for the applications which are both single and multi-process. However, it does not trace MPI. So this really, rocprof-v3 is really a kind of a simplistic tool just for the GPU activity. Its main capabilities are GPU hotspot analysis to identify the performance bottlenecks on GPUs, to also show the device activity through tracing and visualize HIP, HSA, GPU kernels, data transfers, and so on. I remember that 2 days ago there were some questions about the HSA and HIP runtimes, so maybe this tool can help you understand this better. And then also the performance counter collection, so one can collect the counters and then analyze them using rocprof-v3. There is a support for also additionally for Python and OpenMP offload profiling. And if you go to this documentation page, you can find more about rocprof-v3. So how to run rocprof-v3? Well, basically you just load your ROCm module or even ROCm-FR module, and rocprof-v3 should be there. Rocprof-v3 was introduced in ROCm 6.2 as a beta and officially in 6.3. So if you have ROCm version, which was released in the last 1 year or so, you should see rocprof v3. So basically, the way you use it is you specify rocprof v3, then whichever rocprof v3 options you want, followed by double hyphen, and this is very important not to forget this dash here, followed by the application binary and then any application arguments. For MPI and Slurm applications, you typically place rocprof v3 inside the job launcher or also inside the MPI run, which means that you basically specify MPI run, number of processes 4, and then rocprof v3, and then everything else as the above. Output files will then be generated for each MPI process automatically. So you will have, in this case, 4 different MPI outputs. Note, however, that rocprof v3 can be run with MPI, but it does not trace MPI calls. So for tracing MPI calls and MPI activity, you actually need to use the tool that we will be discussing later, which is called rocprof-sys. So how to collect various application traces using rocprof v3? Well, if you do rocprof v3 -help, you will see that there are a bunch of different options. Here we just list a couple of them. And actually, this is quite important, and I encourage you to check those options, because here you would specify what type of activity you want to trace with rocprof v3. So typically what people are mostly interested in are these GPU kernels, so with -- kernel trace. But you might be also interested in the transfer, in the copies, and some other things like cocos and so on. There are also two, and you can of course combine multiple options here. There are also two interesting things. One is runtime trace, which is actually a collection of a couple of different options, notably kernel trace, heap trace, and so on. And then all the way here at the bottom, you see there is also an option of -- systrace, which is exactly the same as -- runtime trace, only in addition, it profiles also HSA activity. So good default is often to use -- runtime trace or -- systrace, because if your run is quite long, then -- systrace might generate traces that are perhaps too big. So then maybe you want runtime trace, or if you know exactly what you're looking for, if you're only interested in GPU kernels, then just use -- kernel trace. So in order to get timeline traces, a currently recommended format is pftrace. So basically, if you want to get the trace files, which you can later visualize, and I will show how, you need to add this -- output format pftrace. If you're interested only in the textual kind of summary output files, by default, until ROCm 7.0, the CSV format was default. So you would, without specifying anything, you would get some CSV files. Starting from ROCm 7.0, which was released 2 months ago, I believe, they changed the default format. It's now some kind of a database format. So basically, in this case, if you still want to get a CSV output, and here in this presentation, we'll focus on CSV outputs, you need to additionally add -- output format CSV. So here is one example how you can collect this. So basically, you specify rocprof v3, and then we say we want to collect kernel traces. So that's why we add -- kernel trace. But we also want to collect stats. So stats option is very useful. I think most of the people use it all the time, which will basically give you statistics of the things that you're tracing in a CSV file. However, note that -- stats always needs to be combined with things that you want to trace. So in this case, we want to collect stats of the kernel trace. If you specify here multiple things, -- stats, kernel trace, and let's say heap trace, you will get stats for both, but you always need to specify something. Then for the convenience, it's very often useful to add this or kernel names, which can sometimes be very verbose. And then finally, there is another option recently added to the ROCm, which is called -- summary or --S, which will actually, on top of this stats CSV files, this -- summary will also print the hotspot summary at the end of your execution at the standard output. So if you're staying in the terminal and you want to see some kind of an overview at the end, adding this dash dash summary is very useful. And then, of course, as I already said, don't forget to add dash dash, followed by your application binary and the arguments. So if you run this, basically you will get a couple of output files, CSV files, including the kernel hotspot summary file, which will be named. The first, you'll have the process ID of your execution, followed by this underscore kernel underscore stats CSV. Actually, if you want to change the names where the by default the output files are stored, you can use arguments of rocprof v3 called dash dash output file and output directory. So basically, if you open now this kernel stats file, it will show you something like this here. So it will show you a CSV file with the name of the kernel, followed by the number of the calls, the total duration, average, and some statistics and so on. Sometimes, especially if the name of the kernels are quite long, it can be a bit cumbersome to look at these things inside the terminal. So you can always copy-paste these CSV files to your laptop and then open them in your favorite spreadsheet viewer like Excel or something like that, where it might be easier to look at these files or maybe even do some basic manipulation. You can also use counters, and to see what counters are available on the machine, you can just check that with rocprof v3 minus capital L. And I think there was a question about this 2 days ago. So there are two ways to collect counters. First one is to write an input file. So basically, here I created an input file which I just called rocprof counters. I mean, you can call it whatever you want. And then there you specify in each line what kind of counters you want to collect. So in this case, I specified 2 lines, 2 sets of counters, and note that why are we having multiple lines, multiple sets of counters? It is because there are hardware limits on how many counters you can collect in a single pass. And here in this case, we have, that's why we had to add all these counters into 2 passes, into 2 lines. And basically the application will be run once per PMC line. Another way to use this is to just specify in the command line option dash dash PMC and then your counters that you want to collect. Basically, this will again generate a CSV file which will look something like this. So here, basically, you will have a bunch of different statistics for each kernel, including the dispatch ID, but also then for each counter that you collected, you will see some metric value. Then when it comes to the visualization of the timelines, so basically, if you collect your rocprof v3, let's say with systrace for all the relevant tracing information and specify output format pftrace, you will get an output file called .pftrace, which you can then copy paste to your local machine and open in Perfetto browser. I believe Giacomo talked briefly about it 2 days ago. And then in Perfetto browser, basically you open this file with the open trace file. You'll see something like here. So basically you will see this is a classical Gantt chart where you see the tracks or resources on the y-axis, and on the x-axis it's timeline. And here, for each one of these rows, you will see certain information. So here, first is the application itself. Then you can see where you can see heap and HPC activity. But also then in this line, compute, you would see the GPU kernels. And then in this copy line, you will see the copy activity between the host and the device. For navigating through Perfetto, you can use WASD key to zoom in, out, and move left or right, or just your mouse as usual. It's pretty intuitive, I would say. And then what you typically want to do is zoom in deep and see the kernel. So here in the compute queue GPU, you would see, in this case, we're running some OpenMP applications. So you would see this OpenMP offload kernel, and you can get more statistics about it if you click on it. Another thing, other type of kernel information that you can get and flow events is also when you click on the kernel, you could also see what was the heap call that was launching this kernel. So following these arrows, these flows, which can sometimes help to debug. Also note that in Perfetto, in the bottom right, you have here this arrow, which I circled in red, which basically allows you to get more information about the selection, about the thing that you clicked on. So in this case, if we click on a kernel, you would there see more information about the specific kernel, such as, okay, the kernel name, but also then the actual duration of the kernel, what were the preceding and succeeding events. There is also some contextual additional information if you want, but also things about the kernel like work size, work group size, and grid size, which can be useful for understanding your performance. rocprof-v3 also allows collecting application traces with rocTX markers. These are specific for v3. You can use the same thing with rocprof-sys. So basically, this allows you to instrument your code and put some markers around the most interesting regions of interest for your application. Here is an example for the C code. So basically what you need to do is in the file where you want to add the markers, you need to include the SDK header file, and then surround the code that you want to track with the push and pop or marking it to annotate. Then don't forget to link when compiling your application with the rock profiler SDK rocTX. And then finally, when you later profile your application with rocprof-v3, please add -- marker trace to collect information about the markers, or you can use some of the options which are already including this marker trace option, such as system trace, systrace, or runtime trace. If you do all that, in your Perfetto output, you will see something like this thing here. So basically, in the top row, you would see the marked parts of the code. So this boundary update and ghost cell update. This is the information that was collected from the markers. And by the way, very similar approach can be done for the codes. So for the rocprof-v3, if you're collecting information from multiple MPI ranks, what you can do later, if you want to see every single rank in a single view, in a single Perfetto file, basically you just need to merge them, and it's very simple. You just concatenate all of these traces, like shown here in the first bullet item, into a single PF trace file, and then you just open it with Perfetto. This will basically give you, in this case, we have an execution with 4 MPI ranks, and you can see that for the rank 0 and rank 1, I unfold to these 2 executions to see all the information, while the Ghost Exchange rank 2 and 3 are folded, just not to clutter the whole execution. So you can, by clicking at the arrows, you can fold and unfold different parts. So regarding the overhead, I mean, like any other profiling tool, the rocprof-v3 of course also has some minimal overhead. It is designed to be really, really minimal in this case, since we are profiling only the GPU part. Few tips for you regarding how to decrease the performance overhead if you see that it's significant. So first, make sure that you're using only the profiling options that you really need. So, I mean, tracing is often faster than hardware counter collection, for example. Also, the number of counters that you collect obviously plays a huge difference, especially if you have these multiple passes for multiple PMC lines. And also be careful if using rocTX markers. So if you instrument your code and put rocTX markers very, very deep inside your code, this can result in a lot of tracing of rocTX regions, which can then result in very large traces as well. In general, I mean, the more data you collect, the more overhead you will have. So just try to find the right balance there for yourself. Note that to minimize the collected data, there is a way, starting from, I think, ROCm 6.4, to profile only a small, interesting part of your execution. And basically, you can do that by using the option collection period, where you can specify when do you want to start profiling, and for how long you want to do it, and also some repetition, if you want to do it repeatedly or not. So basically, this allows you to skip profiling the long initialization of your application, for example, and only focus on a certain period of your application. Okay, so this was rocprof v3. I'm doing with time. Oh, it's good. So now let me move to rocprof-sys. So rocprof v3 is, as I said, quite lightweight and traces only the GPU activity. rocprof-sys is much bigger, and it traces not only GPU but also CPU activity. So it's really a kind of a comprehensive tracing of the applications, and it also has many more different options and different collection modes and so on. So basically, you can do some sampling, you can do dynamic instrumentation, binary rewrite, causal profiling, and so on. There is also visualization format, in this case, protobuf files, but which is slightly different than rocprof v3. But at the end, you can open these again in Perfetto and use exactly the same approach as we described before regarding the visualization and analysis of your timeline traces. The simplest way to use rocprof-sys is just to do straightforward rocprof-sys run, and then, for example, you do add --profile to get the profiles of your execution, --trace to get this protobuf file trace, which you can open in Perfetto. And for example, if you're using if this is an OpenMP application, you should add --include OpenMPT to trace the OpenMP activity. Again, followed by --, so don't forget that one. And later the application with all of its arguments. Of course, to see all the options of rocprof-sys, and there are quite a lot of them, you can always do rocprof-sys run --help, or actually check the documentation. So what I first showed is the simplest way to use rocprof-sys run. Now I will give you a bit more details on what are the other options of rocprof-sys and how to control a bit more what do you want to profile, how, when, and where. So to do that, a typical workflow is to first create a runtime config file. And as I said, this is optional, and this needs to be done only once. But basically what you do is you call this rocprof-sys avail, -G, to get the config file, a textual config file. After that, you potentially want to instrument your binary, and you can do that by using rocprof-sys instrument and create from your initial application binary, you can create an instrumented binary. And then finally, you do rocprof-sys run of your instrumented binary, or of course you can run it with the MPI. Here are the links for more information in the documentation and about the configuration parameters, because there are quite a few. So let me show this in action a bit. So for generating configuration file, as I said, you do rocprof-sys avail -G, and then you specify where you want to save your config file. Then you open this text file with your favorite text editor, and you can check inside. You will see quite a few options. I think that most of them are actually quite intuitive. So for example, there is an option rocprof-sys trace, where you can which you can put either to true or false, which basically enables or disables tracing. Then you can add delays, durations. You can, again, for the profile, you can enable or disable it, and so on. Once you edited your config file, don't forget to call this line here, so to export rocprof-sys config file and the path of your config file. When this variable rocprof-sys config file is exported, then when you actually run rocprof-sys to trace your application, it will search for this file and use the options specified in the config file. So you might have realized that here I'm talking about the config file. In the beginning, I mentioned some rocprof-sys command line options. So there are different ways actually to use rocprof-sys run. So three main ways I would say is to specify things in the configuration file. So for example, let's say we want to enable tracing OpenMP. Well, in this config file, you need to set rocprof-sys use OpenMP to true. Another way to do this is to export rocprof-sys use OpenMP in your environment, and then just run rocprof-sys run. Or a third option is to add, as I mentioned in the beginning, this dash include OpenMPT. So all of these are viable options. It really depends on your preference. Then once you configure things, you might want to do a binary rewrite of your application. So basically there you can instrument what are the functions that you want to trace, because maybe by default you don't get enough information and you want to specify this here. So to do this, you will call rocprof-sys instrument, then -o to specify the output file. Here we call it Jacobi hip.inst, and then the name of your executable. So this will create a new binary called Jacobi_hip.inst with the instrumented function. Note that by the default, the instrumentation will be done only for the functions that have more than, I think, 1024 instructions. And you can change that through different options of rocprof-sys instrument. By, let's say, if you want to instrument all the routines that have more than 500 or more cycles, you just specify -i 500. You can also specify here what are the different specific functions that you want to use, using regular expressions, and so on. There are many options to rocprof-sys instrument. When you run rocprof-sys instrument, you will get an output similar to the things shown here on the right of the slide. So a bunch of logging data, but probably then the most interesting things are here in green, are these paths to different output files. And here, probably the most interesting one is called instrumented.txt, which I encourage you to open and see what were the actual the actual functions which were instrumented by rocprof-sys instrument. By the way, I mean, the instrumentation, this binary rewrite is not always needed. So for example, for the OpenMP applications, if you're tracing, want some basic tracings of the OpenMP, this is not necessary. You just need to specify include OpenMPT. But the binary rewrite can be very useful if you want a full control. So even for the OpenMP applications, maybe you'll want only to trace a subset of these function OpenMP functions, in which case you will use rocprof-sys instrument with dash function include, and then specify here the names of the kernels or the part of the name of the kernels, if you want to use regular expressions, that you want instrumented. Finally, after instrumentation, the next step is to run with rocprof-sys run, or in this case, this is an MPI application. So we do MPI run. Here just one process, a rocprof-sys run dash. Here now we specify the name of your instrumented binary, followed by the command line arguments of the application. This will provide you with the output similar to the one here on the right. So at the very beginning, again, some log information, but then a very good hint is that you will see this kind of ASCII art for the ROCm systems profiler. This means that you're really using rocprof-sys run. And by the way, if you don't see these things on your output, this means that you're probably forgot to add something somewhere and that you're not really profiling. Then this is followed by the output from the application itself. So here we have some output from this Jacobi application about the iterations and residuals and whatnot. And then at the very end of the execution, again, a very useful thing are the paths to the output files, which you can then open in your terminal, or in case of these protobuf files that you want to visualize with Perfetto. Basically, what you need to do is you need to SCP them to your local machine, and this is where this complete path comes very handy, because you can just copy paste it from the terminal. So what are these output files? Let's start with the profiles. So if you enabled rocprof-sys profile through this configuration variable, or by adding dash profile to the rocprof-sys run, basically this will create per MPI rank a single voltlock.txt and also .json with the similar information, but let's stick to the text files, which you can then just open in your terminal or text editor, and it will provide you with the information as the things here below. So basically, it will provide you with different function calls, but then the number of these calls followed by the total duration and different statistics. So this is, of course, very similar to what we have seen with rocprof v3. However, note that here we have not only the GPU activity, the GPU kernels, but also the MPI activity. So here we see some MPI calls and many other things. Sometimes, because by default, this profile will also keep you guard you the call stack and the whole hierarchy, which can be useful, but can also sometimes be a bit confusing, especially if you have many layers of abstraction in your application. Then sometimes it's then easier to add also this rocprof flat profile and just to flatten out everything into and kind of align it for an easier overview of exactly the same information at the end. Then when it comes to the protobuf files, so this trace files, again, very similar approach to the rocprof v3. You copy it to your local machine and open in a browser this Perfetto and click open trace file and open this Perfetto trace here for the rank 0.proto. Here you will see the usual view, so the time on the x-axis and different information on the y-axis. Note that here now we have some CPU information. So for example, here we even have some information about the CPU frequency, which might be useful or not, depends on what you're interested in. And this is then combined also with the GPU activity. Here we see some traces of the CPU functions as well. Of course, you can zoom in again using your mouse or WASD keys and see what's going on. So here we see on the CPU side different heap calls combined with the MPI activity and so on. So here you would see a bunch of other different things. So for example, you can see also the GPU characteristics. So not only the GPU kernels, but also information collected from the ROCm SMI. So what was the temperature of the GPU and when the GPU was busy, the power, and this type of things. There are also flow of the events between the heap calls and the GPU kernels and many more. Also the markers here on the right. So while rocprof v3 is useful for understanding your GPU activity, rocprof-sys, as we said, it really gives you a whole overview of both CPU and GPU activity, and therefore it can be very useful to study the overlap between different compute and communication parts of your application. And look at both what's happening on the GPU and when the GPU is busy, and what is CPU doing meanwhile, whether it's doing some MPI communications or not. Note that with rocprof-sys, especially if you enable everything, you can get really a lot of information. So you can get really a lot of these rows or tracks. And sometimes it can be a bit cumbersome to scroll up and down and to see what's going on. So to bypass this, what you can do is for each one of these rows or tracks, you can pin them clicking here on this pinning button, and then the same row will reappear at the top of your screen. So basically here, in this case, out of, I don't know, 20, 30 different rows, I selected the only two ones that are the most interesting. I pinned them, and then I see them on the top of my screen. And then when analyzing, I just focus on these two. rocprof-sys can also be used to study concurrent kernels and different streams and overlaps. So here we have an example of 3 rocprof-sys timeline views of the executions, which are using either 1 or 2 or 4 streams, heap streams. And here actually on the right, you can see that in this specific example, there was a big gain in terms of performance when using multiple streams. If you're interested in this type of executions, or if this is something which your application is using, I can encourage you to check our example in the usual HPC training examples in the heap stream overlap part of the repository. rocprof-sys can also do sampling of the CPU call stack, and this can be very useful, especially I think for some Python apps, where basically you can specify this by saying that by enabling sampling and then specifying the frequency of sampling that you want to do, so how many samples per second. Or you can alternatively run your application not with rocprof-sys run, but with rocprof-sys sample, which is basically just a wrapper of rocprof-sys run plus plus these couple of environment variables. So this will then provide you with a Perfetto trace, which looks something like this here. So basically, you can see now what are the different CPU calls and how they're chained up one after the other. Of course, you very often want to zoom in to the call stack and see what's going on. Note that this sampling information will typically appear in a row called thread and the number of thread and then S in the brackets. And this sampling very often typically appears at the bottom of your trace. So basically, when you open Perfetto and if you don't see a sampling, make sure that you scroll down to check if it's maybe at the bottom of your analysis. rocprof-sys also allows, starting from ROCm 6.4, to profile network activity. This is perhaps a bit more advanced, but I guess if you're interested in your network activity, then you very often know what you're doing and know what you're searching for. So to use this, I mean, you can first check with rocprof-sys avail what is the NIC information, what are the names of your hardware counters. Then you need to set up a couple of parameters in the rocprof-sys config file. And note also that your perf paranoid needs to be 2 or lower. And I know that there was also some discussions about perf event paranoid 2 days ago. So for this thing, for puppy counters, this definitely needs to be 2 or lower. And then finally, at the moment, to collect this network information, you would need to enable sampling, although this limitation, I think, will be removed soon. So if you specify all of these things later in your Perfetto output and also in your text output files, you would see information about the network counters. So for example, here in the Perfetto view, you would see this type of views showing when there was some network activity. Note that, of course, the overhead can be reduced by increasing actually by decreasing the sampling frequency and by reducing the number of events that you collect. So more details about the rocprof-sys network profiling can be found if you follow this link, or if you just check the rocprof-sys documentation, and there is a specific page about the NIC profiling. Finally, a couple of rocprof-sys tips and tricks. So if you run your rocprof-sys run and you don't see anything in the output, you don't see this ASCII art in the beginning of your execution, first check the app that everything is fine with the app, but then check your environment. So the error that happens the most often, also to myself, I must admit, is that I forget to add this dash between the rocprof-sys arguments and the application. Also, in some Storm environments, especially in the previous versions of rocprof-sys, we have seen that sometimes the incorrect order of the loading garbage can cause issues, or that sometimes there are some failures with sbatch, in which case we encourage you to interactively connect to a node using srun and then just profile directly on the node. Perfetto itself, so Perfetto visualization comes with some known limitations. So there's some max file size, which I think is around 4 gigabytes. But actually, even for the traces which are between 1 and 4 gigabytes, this can already get a bit big for your Perfetto, because it's open in the web browser. So there could be some limits on your tab inside the web browser. And there are ways actually to circumvent this by using Perfetto's trace processor, which actually allows you to load the trace first into the memory of your laptop and then open it from there. Also, and again, this is something we have observed in the past, not that much recently, but sometimes the latest Perfetto UI would not open certain traces, in which case we suggest you to just use the older version of Perfetto. And for me, the version 46, which can be found using the link provided here, is the one that so far worked all the time. Another tip, of course, is to disable all the options that are not useful for your analysis. This would make your profiling faster and the overhead smaller, so the impact on the application is smaller. But also, arguably, even more important, it will not clutter your views inside the Perfetto with a bunch of information that you don't care. So a good example for this are those frequency information about the CPUs, especially since this is done for each CPU core. This can create quite a lot of rows that you probably don't care about. Luckily, this specific thing about the frequencies was disabled in ROCm 7.0, but it is enabled by default in the previous ones. In any case, you can always disable it by using rocprof-sys sampling CPUs equals to none, and the same applies to other options of rocprof-sys. There are some additional rocprof-sys features. So there is the dynamic runtime instrumentation to instrument dependent libraries. There are also ways to profile COCOS, for which you need to enable this rocprof-sys use COCOS. There is also some experimental causal profiling and also some user APIs to control the instrumentation. In general, rocprof-sys, there are quite a lot of development, and each new ROCm release or rocprof-sys release comes with a bunch of new things. And to follow this, to compare different releases, you can always check this changelog here. Okay, so to summarize, what I presented was first rocprof v3. So this is a command line interface tool to quickly analyze only GPU activity on AMD GPUs. It allows for the hotspot analysis to identify performance bottlenecks, the application tracing on various levels, and performance counter collection to analyze kernel performance in a bit more details. And then the second tool that I presented is rocprof-sys. So this is a very powerful tool to understand not only GPU, but GPU plus CPU activity. And it's really ideal to have an initial look on how the application runs and to analyze the overlaps between the CPU and GPU compute and communications. And it really allows you to obtain a comprehensive trace with system characteristics. So a question that we very often get is, okay, which one to use? Well, if you care only about the GPU activity, if you just want to check what is your application doing on a GPU, then go with rocprof v3. It's simpler. It will provide you with less data, but with the data that you're mostly interested in. If you're really interested in the overlap between compute and communication and also checking what's happening on a CPU while your GPU is, for example, idle in certain periods, then you need rocprof-sys. These are some additional resources. We recently published a 3-part profiling guide, and I think Giacomo also mentioned this on Tuesday. And actually, his presentation is largely based on this novice blog. Since this is now the advanced part of this workshop, I would also recommend you to check the advanced blog post, which goes into a bit more details and uses rocprof v3 and rocprof-sys in a bit more details, combined with the rocprof-compute tool, which Bob will present after the break, I guess. Finally, for the hands-on, we have all the exercises are inside the usual HPC training examples. We have a couple of them for rocprof v3 and rocprof-sys. So here I highlighted the tool which I most recently checked and verified for the AEC6. I think the Ghost Exchange, for example, was written some time ago. So perhaps if you want to run it, you need to adapt certain paths and modules, but in principle, it should work. And if you're running this on AEC6, basically it is sufficient to just do module load ROCm 7, and you should see in your path both rocprof v3 and rocprof-sys. And with that, I guess I will stop sharing and take any questions that you might have.
Thanks, Luka.
So I don't know, Giacomo, we really messed up here. You know, this is a really brutal day. There's no break scheduled, no coffee. It could get really scary. So
what have we done?
Fortunately, Luka's helped us out a little bit by ending a little earlier. We'll have 10 minutes for exercises and 10 minutes for coffee or afternoon snack. Anyway, Seema, you want to mention survey and other things?
Yes, we have sent here to the chat the survey, also in Discord. Please give us your opinion about this training. We appreciate your help here. Thank you.
And thank you, Sima, thank you, Luka, and Bob. I wanted to say that the last presentation of the day is probably not gonna need 45 minutes. So if we wanna break and then have you start at 3:15, and then just go up until 4, and then 15 for the exercises, I think 30 minutes for that one is plenty.
Okay, let's do that. So we'll resume at 3:15 after exercises and break.
Sounds good. Thank you. It's warming up here. I might just even, go crazy and open my vest just a little bit. See you later.
Okay, we're back from break, and next presentation is going to be on kernel profiling. Yes, it helps to have a little coffee. Okay, reminder for everyone to go ahead and fill in the survey. It's a fairly quick survey to fill in, and it does help us plan for future sessions and improve the materials. We'll go ahead and start sharing. Okay, this talk is going to be about looking at specific kernels and why you're getting the performance you're getting with those kernels and how to improve them. So rocprof-compute is looks in detail at the data from the hardware counters and then puts it in a form which makes it much easier to understand what is happening on your system. And so it is focusing on kernel performance, so really makes sense on a single GPU to look at that performance rather than rocprof-sys, which we saw in the previous presentation, which is looking more at the interaction of the GPU and the CPUs. And rocprof-compute was added into the production ROCm stack with ROCm 6.3. Before that, it was called OmniPerf when it was in the research group. So we can really use this tool to look at the roofline. That was a tool that we've seen a couple of times already, and that gives us a quick visual overview of what's happening with each kernel. And then we can look at some of the performance numbers for the kernel and compare them perhaps to the maximum performance that we could get for that quantity. And it computes derived metrics that can help you understand further what's happening with the kernel. So again, we talked about the roofline earlier, and we can generate this roofline for our kernels with this tool. And it will also plot the empirical roof lines for the hardware that you're on. So it's not a theoretical, it's an empirical measurement with small kernels that are run to test the performance. And here's an example of the roof line that we can see with rocprof-compute. In this example, we're looking at the ghost exchange problem, and so the compute part of that is a blur stencil where we just add up all the values around us and take the average. And we see 3 dots, one for HBM, one for L2, and one for L1. In general, we focus on the high bandwidth memory performance and the arithmetic intensity. We see the initialization routine has much lower performance, but it's only run once, so we are generally not going to be as worried about that. And so we see that we're actually doing pretty good with this blur kernel, that we're close to that bandwidth line. And that tells us a lot about, how much opportunity there is for improving the performance of that. We also can get a list of stats, much like we did with the previous tools. And here it's going to list the kernels and what ID they have. So this is in ranked order of how much time they're taking. So we're going to use that ID 0 in some of our later commands. So it's good to know what these kernel IDs are. And we're going to store this well, we stored this profile in the first line when we did the no roof option, and we told it to store the profile, and it by default puts it in workloads v1 and the GPU type. So when we do the analysis, we're going to add that -p to point to that location. And you see that v1 comes from the -n v1 in the profile command. We talked a little bit earlier about all the options you can add for the ghost exchange. And so we're just running that example we talked about earlier to get a profile of it. And now that we have, what kernel is taking the most time, we can see the each invocation of the kernel in this file. So for this example, we're going to compare two different kernel implementations. And this is what I find really, really valuable in the tool is the comparison feature. So we're going to first run with the grid and block size that you see in the first line, and then we're going to modify it and change that block size. So we're going to go from a block size of 64 to 256. So what is the performance difference when we do that? So we're going to run a version 2 with that new 256 block size. We're going to store, so it will get stored in a different directory. And we can compare those two versions by supplying two -p options in the analyze command line. So we're going to analyze version 1 and compare it to version 2. And so what you see down in the report is we see the average for each of those, the first one, the second one, and then the difference. And it shows that there's a 2%, approximately 2% difference in the average. And that gives a quick feedback of what the performance is. We're going to look at a few exercises now and use that comparison feature to look at the original problem version and the solution version. There's you can run these examples. It's in the exercises handout, and step through them yourselves. And I do recommend that to get a feel for this tool. There is a lot of output that comes out of this tool, so we're only showing small parts of it. There's a few hundred lines of output, and it takes a little bit of time to know which ones to look at. So we're going to be talking about the most important lines to look at with each of these cases. So the READMEs are pretty comprehensive, so you can go ahead and go through those READMEs. They're in the rocprof-compute directory in the training examples. And this one was done with ROCm 640. If you're working with a different ROCm release, there's going to be changes in the output and sometimes the command line. So
you may want to do -- help and find out what the exact options that are available in the version you're working with. So we can load this Profiler Compute 640. Now I will note we have 641 on the system and 701. For the profiler exercises, it is probably best to use the ROCm 641 version. So we're going to look at launch parameters in the first exercise, and this is going to be a fairly simple code and a fairly common case that we're going to look at for all of these exercises. So let's look at the code that we're working with. So it's a simple kernel that does a vector matrix vector product. So there's a fair amount of compute involved in here, and it's a complex loop structure. A is a 1D array, but allocated as a 1D array, but it is really a two-dimensional array, n by m. And x is a vector of size m, and y is a vector of size n. So the first exercise, we run this compute profile and generate the roof only. So we're only going to look at the roof. This is a good practice to start out with to sort of get an idea what's going on before you dive in and do a very detailed analysis. And kernel names will give you a PDF output showing which names correspond to the icons in the roofline plot. So you'll get a roofline out, and then you get a separate PDF with the list of the names. So we're going to look at these roofline plots. There's going to be 3 dots for each of the kernels. It can be a little tricky to match up the kernels with the dots. So you really want to take a look at that kernel names output, and then you may have some overlapping data points. And you may get different results with different compiler versions as the compiler improves or changes. It may change your performance, so you may not get exactly what's shown here. And so here we do this first plot, and we see very poor performance. And how poor is it? Well, this is a log-log plot, so that's over 2 orders of magnitude below the roof line. And we see 2 dots in this, but there's a note that the L2 data point is hidden behind the HBM data point. And then we see the blue dot is the YAX kernel in our application. That's kind of obvious here because we basically have one kernel, but with multiple kernels, you do really need to pay attention to which one is which. So when we launch this kernel, the problem version has a grid of 4, 1, 1 and a block of 64. And so we're not using all of the GPU compute units. So if we change that to a grid of 2048 and a block size of 64, we'll run that and do a comparison to that first version. And we're going to use the no roof option when we run these 2 profiles. So now we're going to generate the profile without the roof. And that does save some time because the roof line requires more hardware counters than you might need otherwise. So here is our comparison of these 2 runs. And we have in gray, we have the problem and the solution as blue. And so we see in these 2 runs that they run the same number of count of the kernels, and we see the sum that there's a large difference in the sum of that kernel runtime. And overall, there's a 56.6x speed up as a result of this change. So that made a large difference, and it may seem pretty obvious that that we're not using all of the GPU, but in real code, it can be a little hard to determine sometimes what the launch parameters that are used are. And what do we see? We see the most important statistics are in this block 7, the wavefront launch stats. And we see that we're getting a lot more launches when we have that larger grids, larger size in the, that we specified in the problem. And so increased launch wavefronts, which increases that grid size. What does it do to, we'll regenerate the roof line in this case. So our original roof line that we looked at the start and our new roof line. And we see it's, you have to really pay attention that the scale has changed here. So we are much, much closer to the high bandwidth memory here. We're still not, there's still quite a difference here, but we're much closer than the first case. So moving up and to the right is generally what we're trying to do when we work on these performance issues. So there is a lot of output that comes out of the analyze command line, and we can change how much of it is shown with this -- block option to the command line. And so it's only showing those ones we were interested in. Of course, you have to know which ones to select. And so the first time through, you may get all the output and then start focusing on the ones that are the most important for what you're looking at in your analysis. And we often play around with these launch parameters to get better performance. So this is a good way to get a confirmation that you're improving things and not just relying on difference in runtime, but maybe understanding why you're getting that better performance. We're going to look in exercise 2 at local data store. So this one, we're going to allocate some shared memory. And that can be a very effective strategy, but it can also restrict occupancy and how much of the GPU can be utilized, how many wavefronts can be launched. So in this case, we're going to allocate LDS with this shared double temp and specify a large enough LDS value to allocate all of the LDS for this kernel. And then we're going to have 2 solutions where we remove that LDS allocation entirely, or we reduce the size of it. And that's a little bit faster than the no LDS. And so we're going to show that in the output in the next slide. So we're going to go ahead and run the problem and the solution with no roof, collect our data, and then run the analyze command, comparing those two. And we see that we get 1.2x speed up between those 2 versions. So reducing LDS usage allowed the performance to increase. But now what we really want to do is understand why. And so we can look at the system speed of light panel, and we see wavefront occupancy. And we got a pretty good idea that occupancy is what we want to look at, because using too much LDS will reduce occupancy. And so we see here that we've had a big improvement in the occupancy values. And so we've gone from a 2% of peak to 5% of peak. So that's improved things quite a bit. the one panel that we often look at is insufficient, this insufficient panel in the workgroup manager. And there's 4 or 5 rows of insufficient values printed out. And in this case, we see that LDS was blocking the launch of wavefronts. When we reduce the amount of LDS being used, we're no longer blocking the launch of additional wavefronts. And so that gives us this large reduction in what it really is, a stall of wavefronts being launched. So that's showing us what's causing this performance improvement. So we've shown here how this performance limiter of LDS is limiting occupancy, and as a result is decreasing performance. And so we can get that statistic for the LDS with this these block options on the analyze line. And so insufficient resources originally were shown as an absolute value, and they have been changed to percentages. But the magnitude really doesn't make a whole lot of sense to you when you're analyzing it. It's really, if you've got large values in any of them, that's something to pay attention to. So really anything which is non-zero is saying that you have a performance limiter because the wavefronts cannot be launched. So our exercise 3, we're going to look at register occupancy. We've talked in the past that LDS's shared memory is one of the limiters that we often have. Well, the other one is vector general purpose registers. And so there's 3 types of registers: vector general purpose registers, scalar registers, and then these accumulation vector general purpose registers, which are generally used by the compiler for matrix operations or some other type of operations. And if we use too many of those, it will reduce the occupancy and reduce performance. So now we're going to run the problem and the solution and see what happens there. So we get a minor speed up here. And what's interesting about this one is we don't see as big a improvement as we might expect at first. The occupancies are similar, and we see only a small change in this insufficient SIMD VGPRs block. And this is showing how many vector general purpose registers we're using, 92, and 132 of these accumulating general purpose registers. So in this case, with this version of the compiler, this occupancy list is minor. Let's look at the next example here. And you notice here that you can spill registers to the accumulation general purpose registers because we ran out of vector general purpose registers. That's what the compiler is doing for us. We can't specify that. That's the compiler doing that. And let's go ahead and look at the next pattern, or the next exercise, which is a data access pattern. So, and this is, again, we talked about you really need to load data in a pattern which makes the best use of your cache lines. And in a more complex kernel pattern like we have in this case, it can be a little tricky to get that to be optimum. So let's look at how we can use rocprof-compute to see that data access pattern and how it affects performance. So this is a strided data access pattern, where basically each thread is loading values from a different cache line. And so it has to do multiple cache line loads for each stepping through the operations, each line of the operations in the kernel. So the threads are in this picture in the bottom left. They're accessing a different row of the matrix. So if we change that pattern and we have the threads accessing the data in this column here in a contiguous fashion, then we get rid of that strided data. And let's see how that shows up in rocprof-compute. So this is a small problem. It's easier to change data layouts and the access pattern in the loops. It can be much more difficult to do this in a real code. And let's look at running the two profiles and do the comparison here. So we improve our data access pattern and we get a 30% slowdown. So what's going on here? Our hit rate in L1 is actually 75%. So the solution is actually getting much better hit rate in L1, confirming that we have improved the access pattern, but the solution is slower. Our L2 cache hit decreases sharply. So it takes a little bit of analysis to figure out what's going on here. And so let's look at the atomics. So if we look at that row in the output, we see that the atomic latency is higher. That gives you a key that we need to look at those atomics, not memory bandwidth. And so we are starting to get good performance in the L1 cache. That is helping, but then with a lot of atomics in our routine, we're getting a much slower performance. And if we use a shuffle reduction to reduce that atomic contention, let's look at what happens when we do that. So we're still getting a 30% slowdown. So we've improved atomic latency, but we're still much higher, and the performance, the code is running slower. So again, we have to do a deeper dive into what's going on here. And let's look at the next slide, and it's going to go into what the next step in this solving this problem is. And so the atomic reduction is the problem, but more analysis shows that our problem size is just too small. This is a common problem that when you try to do an analysis, you try to do a small problem to iterate more quickly through code changes and profiling runs. Let's increase that problem size and see what happens. Now we get a 12x speed up. And so the L1 performance looks much the same, but we're not getting the contention on those atomics anymore because they're spread out more in memory. And so it took a few steps here to really narrow down what the problem was and come to a conclusion about what was going on. But what I want to point out here is that it would be hard to do this without being able to see these statistics coming out from rocprof-compute. So it's sort of telling us why. That doesn't mean that it's solving the problem. You still have to solve the problem, but you can get a confirmation of what's happening at the low level in each kernel. So this is summarizing what we've just done. It does help as you start running rocprof-compute to narrow down and focus on the key parts, just the kernel you are interested in and just the blocks of output that you are interested in. So specifying a subset of these metrics can reduce how much output you have to mentally go through. And if you want to get, some information about what block strings you can filter by, there's a help menu for that. And there is a very detailed performance model document that goes into deep detail about what each of the output numbers actually means. And sometimes it's a little bit complicated what those numbers actually represent. Obviously they've gone to a great deal of effort to try to make them represent what you think they are, but it's good to look at the details to understand it in more detail. And so, it does take multiple runs to start understanding what's going on in your application and why you're getting the performance you're getting. Generally, you really want to focus on a single GPU run. How to make this make sense with MPI is being explored. And if you're trying to figure out where to start, looking at, whether all the compute units are being used, what is blocking wavefront launches, such as vector general purpose registers. And if that's the case, you may try smaller workgroup sizes. And then look at, what is your limiting compute operation that is in the code. Is it integer? Is it floating point? Is it double precision? Taking a look at that is actually very helpful because it may be something different than what you're thinking it is for your code. And even if you don't think you're doing any integer operations, especially with 6-dimensional physics calculations, it could be in the index calculation. So that can help point you to where to do some optimization. This can really help you dive down into the kernel and understand overall, why it's getting the performance that it is. But you still have to do a lot of analysis and understanding of your code to really use this and get good results out of it. There's also some other things that are output by this tool, and then you can that we haven't gone over if you want to look at the documentation for it. But first, I would suggest use these training examples and test them out. We've sort of walked through a few of them, but there's more that you can look at. Okay, I think that ends this presentation. Okay, so there's some good questions here. So Adam is asking why there were atomics to do a summation in the inner loop in this case. And that is going to cause a contention for that memory address and slow it down. And since L2 is where those atomics operate on this particular GPU, that's where we see the latency occur and the slower L2 performance. The integer operations, a lot of people don't realize this, but GPUs and CPUs have to do index calculations, and generally the CPU is designed to do an integer calculation at the same time as it does a floating point calculation. So for 2D matrices, you know, it can keep up with the amount of index calculations that are necessary. If you got 6-dimensional, you got a lot more integer operations. So the integer operations will end up being your limiter, not the floating point. On the MI200, that GPU could not co-issue integer and floating point in the same cycle. The MI300 series allows the co-issue of integers and floating point, and so it has less of a problem with the integer operations. But I think a lot of physics application developers say, well, I got a 6-dimensional floating point, heavy floating point physics here, and they're surprised when the integer operations tend to show up as the limiter. And it's because you're doing 6 index calculations for every 1 floating point operation, or something of that sort of ratio. Okay, we're a little over the presentation time and into the exercise time. Well, I guess we started late. And so, Giacomo, you want to start the next presentation at 4:15?
Sure, yeah. I think that's gonna be plenty of time.
Okay.
It's just kind of the cool down.
Yeah. Yeah, and when you run these, you know, we try to make these examples fairly quick to run with as few steps as possible to compile and run them. I do suggest look at the differences in the code to really understand what's happening. Even though you could skip that because we've made it easy, it's still really, really helpful to look at the code itself.
And let me just say that since today is the last day, you know, this is the time for you to ask all the hard questions. We will be monitoring the Discord chat also for the next couple of days, but you know, just want you all to make the most out of this time that we've got together. And also feel free to find us on LinkedIn, keep in touch. You know, we're not gonna disappear after this. If you have questions, you can always shoot us an email or a message on LinkedIn. We'll be there to answer your questions.
And I'm going to remind everybody that you can get all of these slides in the guides channel. It's not sharing. So in this guides channel, you'll see all the PDFs for the slides. But you'll also, if you go back up, there are these exercises documents, so we can go in there and pull up the exercises we've been talking about. And you can download those and work through the examples on your own time. Later, if you don't have time to go through them now, you can save them and look through them later. Let me pull up the exercises. So here's the PDF version of the exercises. And we've been doing the performance profiling. We start out with the intro that we did on the first day, but if we keep going down further, we see the rocprof-compute. And it steps through exactly what the slides did here. And then there's an additional exercise or so. So you can step through this and see how it looks when you generate it. And we see the output. This is the output. You see it sort of
Bob, sorry, I think you're not sharing your screen.
Okay.
Yeah.
Okay. I gotta always click like more than I think I have to share. So here we see the output from the tool, and it's in this
ASCII text output with different rows showing the different parameters. And if you don't specify anything, you'll get hundreds of lines of these. And so that's why we showed once you figure out which blocks are most important for you, select through those to get only that output. So you can step through these exercises one by one on your system. Okay. And remind you that you can download all of those in the guides tab in Discord. If you don't have access to Discord, you can see all of these are from READMEs in the HPC training examples that we've been talking about.
And sorry, Marie or Sima or Vlasta, whenever you can you please make Jose a panelist as well, because he'd like to say something at the end. Thank you. And in the meantime, Bob, there's a couple of questions on Discord, if you want to take a look at those.
Okay.
One is for multi-dimensional grids, how would one reduce the number of integer operations?
That's a good question. At some point, there are so many integer operations necessary, but one trick is to, on the inner loop, compute the pointer to the array values for that inner loop, and then you have a 1D index for that inner loop. And if you do that for each of the loops, it reduces the number of integer operations. Now a compiler could do that as well, and so your compiler might be doing that, but in many cases it's not doing that. So you can do that operation manually. You can also, sometimes you can make it basically a 1D loop, right? And just operate it over all the values, depending on which part of the matrice that you're actually computing on. So by treating it as a 1D array, you only have one integer operation to load that data value. There's a question about rocprof v3-PMC flag. I don't know, Luka, is that one you want to take?
Yeah, actually, I'm searching now for appropriate documentation, so I will come back to Mark in the Discord. I'm pretty sure that there is a page documenting this, but I cannot find it, so let me work on that.
Yeah, I'll go back to Adam's question there. So let's say we have a 6-dimensional array and we want to initialize it to a value. We don't have to use a 6-dimensional loop to do that. We can just go from 1 to the maximum of all the dimensions in a 1-dimensional loop and initialize it. And the compiler can often optimize that into a more optimal memset call instead of using a loop.
And we're also interested in any suggestions or challenges that you've experienced during this event. Not considering the login troubleshooting experience, which is always kind of awkward to deal with, because everybody has their own issues, and we have some issues at times too. So, but we're interested in learning more, if you used which software on the system that we installed you've used, if there was any software that you wanted that you didn't find and you had to install yourself, if you played at all with the different rock conversions that we had, if there was one that had what you needed and one that didn't have what you needed. Anything that you want to share with us, we'll happily take in. Thank you.
And it'd be very interesting to hear, did you try some of the exercises? Was that helpful, having a place to do the hands-on exercises? I'm going to answer Mark's command, or Mark Klaska's question here a little bit. So rocprof-sys does have the PMC options, but they're kind of buried in and automatically generated by rocprof-sys. So it's still accessing the hardware counters, much like rocprof v3. You do not need to use PAPI to do that. It's getting it from Rock Profiler SDK or database, depending on the version, the same as rocprof v3 is doing. But how to generate that -- PMC, we do have to dive into the documentation to see how to change that.
Yeah, so I'm also searching. I cannot find a page in the documentation, although I was sure that there is one. But basically, I'm pretty sure that with rocprof-sys, you have environment variable or this config variable where you can specify what you want to collect. And then underneath, it will use the same approach as rocprof v3, as Bob said. It will rely on the rocprofiler SDK to collect this info.
Now, you do have the option with rocprof-sys to also use PAPI in addition to that.
Yeah,
But
yeah. And again, if you're interested only in the GPU hardware counters, you probably want to go with rocprof v3. But I mean, if you want to use rocprof-sys for other reasons, then for sure, your question is legit.
yeah, and one of the problems with rocprof-sys is that it sort of automatically generates those PMC counters that it's going to collect, and so it may be quite a bit more than what you might have to do in rocprof v3 if you know what you're interested in. So rocprof-sys might be a lot slower to run. And Luka, did you mention the issue that, you know, if you do not have a deterministic code, what happens?
Well, this is more for the rocprof-compute, Bob, so this was your presentation. But yeah, I mean, this is so this is related to the rocprof-compute, that some applications, especially Python applications, the issue can occur if the execution is non-deterministic, and then with rocprof-compute, when it runs multiple times the same application, if it doesn't run the same thing, there could be issues. And actually, we're working on finding kind of a permanent solution. There are some hacks, some workarounds which we can help already now, but developers are working on a more permanent solution there.
Well, they can only solve it so far.
Yeah, exactly.
Because if you have a random number generated option in your code and it's going down a completely different path and it's doing multiple runs to collect all those hardware counters, even with rocprof v3, it may get very confused. So all the tools are subject to that to some degree. Now, what happens, sometimes you may think you're deterministic and you may be near deterministic, but you can get enough variation to cause the tools to fail. And that's what they're trying to resolve, is to eliminate those kinds of failures. If you're getting completely different runs, there's not much they can do. So you might think about that when you're doing something like an LLM where it's by purpose, not deterministic. How do you get valid results? Okay. Yeah, Christina's got a good question. Is there a cheat sheet for the hardware counters? Well, one of the real difficulties for the profiling team, as well as us, is that the hardware counters are different on every piece of hardware. And so the best place to look is to use the help option to list all the hardware counters.
Yeah, so for rocprof v3, you can do rocprof v3 minus capital L, and you'll have the list of all the counters. You can also find the documentations and so on. I think the biggest challenge here is not to be overwhelmed with too many counters and to know which ones to look at. So getting the list is not hard. Figuring out which ones you want, if you don't in advance, is difficult. Yeah. And that is why perhaps if you're looking at the counters, if you're interested in analyzing such details, you probably want to go with rocprof-compute, which is already doing some derived matrix and so on. Unless you really know what you're doing, in which case you know what counters you want.
Okay, we're reaching the start time for the next presentation. We'll remind you again that to do the poll, Seema, you want to go ahead and take it from here?
Yes, please take 2 minutes of your time to fill out the survey. We receive few answers. Please, for the ones that attending this workshop, it is very important for us for improving the training. And also we are planning to give certificate of attendance. Please DM me if you would like to have certificate. Meanwhile, please have 2 minutes for the survey. Thank you.
The videos will be available in the future. It does take some time to generate those, so have a little bit of patience there and check back in a week or two. And we should have them up. And that's greatly appreciated because it's a lot of work to take the video stream and edit it down to the appropriate amount.
And Sima, you know, if you find any good filters to apply to us to make us look better, more awake, younger, anything you can give us, we'll take.
No rabbit ears.
Sunglasses, you know.
Try to look cool. So Giacomo, I think go ahead and set up, and
Yeah.
we'll move to the next presentation.
Okay, so this one is the last presentation of this event. Thanks everyone for sticking with us until the end. But the good news is that this presentation is pretty light. So as I said before, it's gonna be the cool down for this workout here. And the goal is to basically just give you a quick and easy walkthrough of what other tools are available in the HPC community that you might want to use, because you know our tools are getting better and better by the hour, having more and more capabilities. But sometimes the capability that you want, it's just not there, and so you may want to use other tools that have that. And we have appended 2 more mentions of tools to this presentation that are from AMD actually, but since they are being developed right now, we didn't want to include them in the list that we've shown before with the official ones, let's say, that are up and running. So this the last 2 that you'll see, they're from AMD. You know, they still belong to the HPC community tools set, but they are developed by AMD, and hopefully you'll see them getting used more in a more widespread way in the near future. Okay, so basically being more explicit about what I'm gonna talk about here, you'll see that there's a list here of tools. The ones that will look at in a little bit more detail are the ones in orange, so Tau and HPC Toolkit. So Tau is developed at the University of Oregon here in the United States, and it has a long history of being out there. It's great, has a lot of functionalities, and we'll take a look at some of those in just a bit. HPC Toolkit is also from the US here, from Rice University in Houston, Texas. And then there's tools that are from the EU, such as Scorpy, Liquid, Scalask, I think, is also from the EU. And then there are others that are more on the visualization side of things, such as Grafana and Perfetto that you've heard so much about already. And the last 2 are from AMD, and well, Omnistat has been around for a bit already, but rocprof Trace Decoder and HPC Compute Viewer are actually some pretty brand new tools that we have in our toolkit that hopefully will be adopted more in a more wide fashion soon. Okay, so talking about Tau, as I said, it's developed at the University of Oregon, and it's scalable and flexible, and it allows automatic instrumentation through PDT, which stands for Program Database Toolkit. And we have a script to install Tau in our HPC training doc repo. So you basically, if you look at the script, this is the most relevant part, I would say, and we clone from the public mirror on GitHub. So it's this address over here. And right now we are using a specific commit because Kevin Huck is in our team, and he used to be at the University of Oregon working with the Tau team, and he advised that that commit is currently a good one to install from, but we might change it in the future. But you know, the script works in a way that as long as we just update this git commit variable, then everything else will work. And so notice that here there is some highlighted lines, because in the past Tau was basically dividing up the options as rock tracer and rock profiler, because that was matching what we had at AMD in terms of libraries for the tools. I think I talked about it on day one, but now that we have rock profiler SDK, then for newer versions of ROCm, Tau will rely on the rock profiler SDK as well. So that's captured in the installation script. And then notice that Tau creates a library for every configuration that you supply. So if you look at the script, you'll see many lines that look like this that try to kind of cover like what combinations we think might be of most interest. So see here that in this case, we are supplying the MPI, OMPT, OpenMP, PDT, and ROCm. And one more thing to notice, oh, well, by the way, yeah, this ROCm flags here is kind of like a compact way to include all of them. And you see they're up here or up there. And something else that I'd like to point your attention to is that for the C and C++ compilers, we're using the AMD compilers, but there currently is a known issue with using AMD Flank compilers, and therefore for Fortran, we're currently just using gFortran. So there are two main approaches for using Tau in your application. One is to use the Tau wrappers. So basically, the wrapper will replace the compiler with this script here. That you run the script and then it will replace the compiler. And the other way is to do dynamic instrumentation, where you basically have to supply the options that you care about, like here. And for that, you'll be using the Tau exec binary. So there's an example in our examples repo that basically is intended to just check the installation of Tau. So see that we are loading ROCm, OpenMPI, and Tau. And then basically there are these two environment variables that you'll have to set to tell Tau whether or not you're interested in profiling or in tracing. So if Tau profile is 1, then you'll be doing the profiling. If trace is 1, then you'll be doing the tracing. And so see here, there's the example that I was showing you before with the ROCm version. So if the version of ROCm is higher than 619, then you'll be using the rock profiler SDK for Tau. And if it's lower than that, then you see there's rock tracer and rock profiler. And this is exactly the command that I was showing you in the previous slide. And notice that this is running the Jacobi example that you've seen already. So this is something that may be familiar when you see the output. Notice here that I don't think we talked about it, but you can actually get the version of ROCm by basically looking at this file here that's in the ROCm path, and then it's hidden. You have to look into the .info, and then version will tell you the version of ROC. So notice down here that there's this pprof call. So pprof is actually what you'll use to output the data that you got from running tau exec. So an example applied to Jacobi will look like this. And notice the syntax here. So you see node 0 here and thread 0. So thread 0 is the CPU for tau. So this is just some tau naming convention. And here you can see all the activity that happened on the host side on the CPU. So MPI, the heap API, and so on. And if you continue looking at the output of pprof, you'll see that there's a thread 2, and that is actually what happened on the GPU. So you see the kernel that you know everything about now, norm kernel 1 is here. We saw that in the first day, and then there's the other kernels as well. You can also visualize with some GUI tool your output by calling paraprof, and you see you'll get an output like this one that is pretty similar to what you would use in Perfetto with the usual rectangles for all the events and durations. So that's also an option for you, but you'll have to make sure that the GUI is enabled from your terminal. And there's also this cool feature that basically when you're running with MPI, it tells you the 3D communication matrix. This is with Windows though. You can also get with Windows the call graph. So basically see here the different colors refer to the time that it took. So more time than others is in blue here. And if you go back on the arrows, you can see what called the rectangle the arrow is pointing to, the call graph. Okay, and if you are doing the tracing, then it will provide a trace that you can open up in Perfetto, like you would normally do with rocprof v3 or rocprof-sys, as you've seen already, and you can see the CPU activity, GPU activity, and you get a trace basically for each MPI rank. You can also merge them here with this tau3merge.pl command. And so there's also this tool from tau that helps you identify the hot loops for the CPU. So that is particularly helpful if you're trying to port your CPU application to GPU, because then that's gonna tell you the information that you need to identify which kernels are the highest priority to be moved to the GPU, because you'll see the ones that take the most time, and those are the candidates that you'll port first to the GPU. So this is similar to what we've seen with rocprof v3, though there we already knew that we were going to look at GPU kernels and we were looking for candidates for optimization. Here, everything's on the CPU and you're looking for candidates for porting, basically. So it's like the step before that one. And tau also supports Fortran plus OMP offloading. So this is just an example with a code that's called neckbone that's intended to show you here what it looks like in terms of activity for OpenMP offloading here. Okay, so for what concerns HPC toolkit, we said that it's not developed by AMD, but it's a pretty good tool to use because it has several capabilities such as the usual tracing, profiling, and analyzing parallel programs. It has low overhead, and also it does not need instrumentation or recompilation as long as you included the -g flag when you compile. So that's a good feature. to have. And then it supports threads with pthreads and OpenMP, as well as MPI, hybrid frameworks, and GPUs, such as, of course, AMD GPUs. So we've got a script to install HPC Toolkit as well. Right now, it's not installed on AAC6 because there was an issue with a download during the installation that we couldn't get around. But I think maybe by now it will be solved, and you could install it on your home, for instance, with our script if you want to test it. But basically, what is important to know is that the installation relies on a build system called Mason, which I haven't seen used in any other instances. You may have, and you know, it uses this Mason setup framework where you have to specify a few options, such as the -d ROCm, and set it to enabled to leverage the ROCm from HPC Toolkit. This here is just a bird's eye view of some of the features that you can exploit from HPC Toolkit. And if you want more detail, just take a look at this PDF here from which this image has been borrowed. And for what concerns the usage of HPC Toolkit, excuse me, normally you would start with HPC run that will get you a profile and traces if you want. Then you'll move to HPC struct, which will analyze the program structure of your CPU and GPU code. And then you'll do HPC prof, which will interpret the profile. So, and you know, if you want to take it to the next level and use a GUI, then there's HPC viewer as well, which will visualize the results. So again, in our training examples repo, we have three examples or three tests that we use to test the installation of HPC Toolkit. And you see that they are building in the way that I just described, on top of each other. So it starts with HPC run here. And basically the way we run it is this, with this -e CPU time, -e GPU equals AMD. And then it's gonna produce this file here, HPC Toolkit -compute and something else. And then once you've done that, once you tested that HPC run works, you can test HPC struct. So basically HPC struct will get, sorry, that's actually multiple files, as you can see from the star here. So HPC struct will get as input the output of HPC run. And then taking it to the next level, you can also use HPC prof that will produce this database file. Okay, so the last couple of tools that we wanted to mention, these are from AMD. And the first one is this rocprof trace decoder. So don't get intimidated by this image here. You can already tell it's gonna be a lot of information. But you know, if you got into this point, this is what you want. You wanted this, remember. So basically, the additional capabilities that rocprof-compute viewer will give you is the ability to look at what happens from within the kernel. So you've seen how we built this up. We started with rocprof v3, looking at the hotspots. We used rocprof-sys to get a holistic view with CPU, MPI, maybe OpenMP. Then we said, all right, we got all that info. We want to optimize specifically the hotspots because that's how we're going to get the most performance. And for that, you used rocprof-compute. And the next thing, which is even more advanced, is to actually look at what happens from within the kernel. So in particular, we're going to be looking at what lines in the code in the kernel are taking the most time, if there's any stalls that are happening because data has to be waited on, and also what parts of your code are using, for instance, the LDS memory. So basically there's this high level view here with the summary that you can get. And there's also this instructions view that basically will have the code on the right and then the instructions on the left. And then there's other cool data that will show you the wave states, timeline, the occupancy, the hotspots. So as I said, this is a lot of information that, you have to be prepared to browse, but this is really, really useful if you really want to get deep into what's happening inside your kernel and optimize even more from that. Yeah, so here basically we're giving you a little bit more detail on that screenshot that I've shown you before. So I said, yeah, the lines of code from the kernel are on the right. And to the left here, you can see the resources that are used for that line. So that's pretty cool. And basically here you get the assembler ISA and some other information. So, if you want to dive into this, you're gonna have a lot of fun, I'm sure. Last but not least, there's OmniStat, which is also an AMD tool. And this tool is primarily intended for HPC cluster administrators because it can give you a lot of information on the health of your system, such as GPU utilization, power. They used it a lot for power monitoring, for instance, because, the power you use to run your GPUs has an impact on performance, and for environmental reasons or any reasons, you may not want to use the maximum allowed power, and so you may want to use a reduced power. And with this tool, you can kind of monitor what happens in those scenarios. Yeah, so if you want more info on OmniStat, there's dedicated documentation. It's open source, so the source code is up here, and I think that's all. A little cool down here.
Giacomo, I think you're the only person that thinks diving into the details of kernel and the ISA that's generated is a cooldown. It sounds like a dive down to me.
Yes, that makes sense.
But no, it is a good, it's just been introduced in ROCm 7.0, so, and will be improved in the next few releases. So it may be something you want to, if you're really looking at the details, that may be something you want to look at. I think we have, Jose wanted to do present a few slides to the group before we close.
Yes, so this will be quick. Let me share my screen, please. So this presentation, it basically is not, I think it is something you already, you have some idea. But what you need during this presentation has everything you need have been presented by my colleagues already. So here I just want to give you some idea about some best practices when playing with real life application. So generally, if you look at the training, what we did since these few days, it has been about using some kernel, some example to demonstrate, how we perform different kind of activities like profiling and things like that. But in real life, we have a big application to work on. So here, maybe the idea is to port application or to move application on the AMD GPUs or to improve it. In general, we have 6 phases. And one is where we evaluate needs. The other one is we do initial benchmarking, we profile applications, and we port them, optimize, and then we move to advanced optimization. And when you are doing all of these, you have to you need to make sure that your application builds, run on GPUs, and produce correct results. And also, you need to make sure that you are getting a good performance. And that is where you will need to do some runtime. You will need to get some runtime report and also do some performance investigations. So all these tools that I will be talking about here have been presented by my colleague already. And here we are just putting them together to give an overview to our audience here who are maybe software developers, software designer, or part of optimization group as well. So during the runtime report and performance investigation phase, we have there a common methodology, a common idea that we need to keep in mind. One is that when you start that phase, you need to collect the target machine characteristic. Profile your application, maybe starting with something that is simple, a single GPU, single rank, or MPI rank, or single OpenMP numthread, and then move to multi-MPI rank, multi-GPUs, and things like that, and proceed to data analysis. And while analyzing this data, maybe you will go back and start again the process because you are not happy with the performance you are getting, or you are very happy or something. You want to investigate more and know what is going on behind the scene. So generally, to get the ROCm on AMD GPUs, for example, you can use ROCm info to get it. Basically, it is a command line that you see in other presentation already. So we won't go through this detail, but it is something that is available. You need to know your target hardware, the hardware where you want to get the best performance from. The other thing is that if you look at some of the Joanna or Giacomo presentations, they talk about environment variable. So when you are doing some runtime or performance investigation, this environment variable is important and will be necessary depending on the situation you are. So, for example, they talk about a libmp kernel trace where you can set to 1 or 2. You also have another one that is AMD log level. From 0 to 4, you can set this variable. And if you are working on AMD HPE system, you might need to set some KAC debug. This is another variable as well. So it depends on the software stack you are using, and it depends on the hardware, on the goal you want to achieve via the performance investigation. And we have plenty of these variables. So another is libmp target debug, where you can set which you display offload runtime debug information. You can set profile, libtarget profile, libtarget info to different kind of value. And what is interesting here is that we have plenty of variables that you can use to do just initial profiling and make sure that, okay, my code is really offloading, my code is executing, is transferring data between CPU and GPU, and so on and so forth. What is interesting, another thing interesting is that outputs depend on every compiler and environment variable that you are using. They are not providing the same information. So you might test, you might need some variable, you might use some environment variable that is not exactly what you are expecting. So you might need to change when you are doing performance investigation. So I will give an example that is based on what Giacomo showed a few days yesterday. So the SASP example here is just an OpenMP example that we work on. And if you see, for example, you set this equal 1, you get a certain output. That is not exactly what you get when you set the same, you export this, you set that to 2, this environment variable to 2. So if you have a whole application and you are doing a performance investigation, the information that you will get out from this by setting this variable, this environmental variable will depend. In fact, it depends on different kind of factors. So if you set, you can get a huge amount of data outside of outside of your run, or you can get small amount of data and it is sufficient for you. So it depends. It depends on the case. It depends on the goal you have in your minds. And another example, let's say that, okay, you are doing a performance investigation and you want to compute, for example, you want to know what is the bandwidth achieved between CPU and GPU while transferring data. You don't know, but you don't want to use a heavy profiling tool right now, but you can set environment variable and get some information. Here, for example, if you set this, it will get this is saying that, okay, we have some data copying from host to device with the size of the data. We also have data copying from device to host with the size of the data. And so we have this. So you can see that when we change parameters and run the same kernel or application, it will give you another size. So we know exactly when data transferring is happening between CPU and GPUs. As soon as you know when this is happening, you know the size of data that has been transferred between both, and you know the duration of these activities, you can compute the bandwidth achieved while running your applications. The bandwidth achieved between CPU and GPU while running your applications. So environment variables are first key element that can help you doing your performance investigation easily. Here I'm showing another, for example, if you set this kernel trace equal to with and you run the same example, you have a duration of each activity that is happening. You know the type of activities that is happening. You know exactly when data are moved, data have been submitting, and here you have data retrieved that tell you that, okay, we are moving data back from GPU to CPU, and it takes 60 microseconds. And all of this together gives you the execution time of your application when you run it, when you time it. For example, you want to know, okay, in average, what is the duration of my application? So we can go for different examples, but just to say that, okay, environment variables are really your first guide that can help you when you are doing a performance investigation. Now, after the performance investigation, you want to go more, you want to go deeper, you want to understand more what the application is doing. That is where you have a combination of tools. You do the profiling on AMD GPUs. You can profile AMD GPU, GCD, or XCD. So that is where you will get the kernel background, get a kernel breakdown timings. You can collect hardware performance counter plus statistic. You can get all these logs. So when you are doing this, you need a tool. That is where you need to like rocprof, HPC community tools. Rocprof, for example, you can activate, you can use the stat, you can use heap trade, you can do hardware counters, as we learned from Luka presentations. And then you can go after doing a single AMD GPU's profiling and look at analyzing this data. And if you want more, again, you can do next the profiling in multi-processing context. And here you also have rocprof, and you can use other tools as well. MPI trace, for example, is not AMD tools, but people can use that to track what is going on MPI call activities, what is going on, and how much time it costs to do the communications. And again, HPC community tool that Giacomo talked about will be useful here as well. So to summarize this, it is really important, to know the goal that you want to achieve. And especially in the context of performance investigation, it is not something that is always straightforward. You can continue improving your code as soon as you want more performance. So the transition to GPU should be effortless, and the application migration require a different process. You need to know the process, of course, but you also need to the compiler. You need to map a compiler name, for example. You need to map compiler options. You need to do effortless code tuning. And at every step, we need to make sure that the code built, run on GPUs, and produce correct results. Result and performance collected just after application migration are used as a reference for further code tuning and optimizations. And also, environment variable can be used to control and get more information about offloaded kernel from your application. You have a whole application and you want to have a quick idea about what is running on the GPU, what is going on, and things like that. Environment variable can help you easily. And that is why it is important to learn from the target compilers. It is to learn from the variables and to learn from the debug information that you have. Another thing to keep in mind is that when you are doing the offloading, you need to design it in a way that it is efficient on your accelerators. It might require some algorithm tuning, but as you know, when you profile application, you know big hotspots, and you also have additional hotspot that is maybe not worth offloading because the cost of offloading this kind of hotspot won't be work profitable for your applications. So that is why it is important to design the offload when you are offloading your application, to design it in a way that the application take advantage of the full parallelism that the GPU you can get out of the GPUs. If the algorithm or your code is not well tuned, or the code is CPU based code and it's not well adapted to the GPU, you can change it in a little bit in order to take advantage of the full parallelism. Just keep in mind that GPU is used for massive parallelism. So you have a lot of compute unit that are available and you can use for your application. You can use to get great performance for your applications. So always offload important application. If you are doing OpenMP, you can use OpenMP team construct to exploit the whole machine. And one important thing is that you need a best performance. You will get best performance generally when the software parameters match your target AMD GPU's hardware characteristic. Because you have software. When we say software parameters, is that okay? If you are using OpenMP, let's say you are using OpenMP, for example, you have NumTeam, you have stress limit, you have different kinds of parameters. That my colleagues, they already talked about that before. So you have plenty of parameters that are available. So if you are able to match the hardware characteristic, then you will generally get best performance out of it. When we talk about hardware characteristic, as we said, hardware characteristic, you can get it by using RockMinfo. And for hybrid HPC AI application, it is important to go beyond a single GPU profiling. So you will need multi GPUs within a single node, or multi GPUs outside of a single node. So this means scale up, scale out. And multi GPUs on AMD system should work without requiring code change. If your application support is designed, it is a hybrid application, MPI, that use MPI OpenMP, for example, multi GPU should work directly. So once you are sure that this is working, next you can optimize MPI communication between GPUs. And here, maybe distance between GPUs might be important depending on the situation. So that is the thing I want to share with you guys. There are other things that are here, but it is not, I think, the key message is what I already delivered. So thank you.
Thank you for wrapping up that, Jose. I'm going to quickly share the slides on additional AMD training resources, and then we'll be wrapping up. So there are quite a few other resources you may be able to use to explore programming the GPUs further. So I'm just going to go through these very quickly. We do system administration training, as well as this training workshop format that we just did. And we do hackathons at various sites. That's usually an on-site event of around 8 teams. And generally, you want to have a code that you've been working on a while and have questions about before you go on to a hackathon. And you can
check with us if you want to schedule something like that. I want to point out the lab notes and Rockham blogs that some of our team members have created. So that's at gpuopen.com or rockham.blogs.amd.com. And so there's detailed blogs on different topics that they have developed. And here's a short list of the many of the different blogs in the HPC topics. We also have a lot of AI topics that have been posted. There are a lot of videos online. We have some from the Edinburgh Parallel Computing Center training and YouTube. I think the best summary one right now is HLRS in Stuttgart has posted slides and recordings from presentations for the last couple of years. Oak Ridge keeps a list of prior presentations, and we've been doing a number of those over the years. And for the latest ones, these are from a while ago. So to see the latest ones, go to their training archive. NCCS in Sweden recorded some of our sessions. Those are getting to be a little bit dated at this point. We also have a lot of documentation on the Rockham Docs site. We pull that in also for our AI programming assistant, but you may search there. It is getting more and more documentation and often has answers to the questions you have. It's just finding the information that can be a little bit difficult. The developer site has a bunch of videos. There's also a HIP programming book, and the Oak Ridge site has some really nice materials that they have developed for their system. I also want to note there's some books that are useful. The HIP programming book is very good resources for using the HIP language. I do want to call out this new OpenMP GPU programming book. A lot of the OpenMP books do not really talk about GPU offloading, and this one is recent enough they spend some time on that. And then, of course, there's my book that I co-authored with Yuli Zamora that has a broad coverage of the field of parallel and high-performance computing. And that's it for those slides, and I'm going to conclude here and see if Giacomo has any wrap-up, and then Seema.
Thanks, Bob. Thanks, Jose. Thanks, anyone in our team, the CASTIEL and CC. I don't remember the full acronym. I'm just going to say thanks, Marie and Karim. Easier. Thanks, everyone that attended. It's been a lot of fun, and we're grateful for the opportunity.
Thank you very much, Bob, Giacomo, Jose, and Luka, for this great event. As part of CASTIEL project and together with NCC France, we would like to thank you, the AMD team, for this great effort. I know that the time zone is a bit challenging for you, but it is really appreciated. Also, thank you all for participating in this training event. I hope you enjoyed it. I hope also you had time to fill out our survey. That is, your feedback is very important for us. Yeah, cross the fingers for receiving more feedbacks. The videos will be soon available, and also certificate of attendance. If you need any, please DM me. Meanwhile, you fill out again the survey. So this is wrapping up our 3 days event. I hope you are going back with full hand, and thank you very much, and see you next time, hopefully. Thank you very much.
Thank you.
Thank you, everyone.
Ciao.
Sima, grazie mille. Ciao a tutti.
Gracias.